Dear students, let us continue our discussion on logistic regression. We have seen in the previous lecture that we have to maximize the probability likelihood of yk given xk as formulated here. We have also seen that the HW of xk here is given by the logistic function, which is e power minus double A transpose xk. And this is evaluated. This probability is for only one sample. We will see how to update the weight vector for or the weights corresponding to each feature that maps to the output binary value, in this case, for a single sample first. That will give us a stochastic gradient descent rule to update the weight as through this. In general, we have discussed about gradient descent. However, here what we are trying to do is maximize the probability or the likelihood, and thus what we use for performing the optimization or the weight update is gradient ascent. As the name indicates, gradient ascent essentially does exactly the opposite of the gradient descent in terms of movement based on the derivative or the partial derivative with respect to the cost function. So it tries to move towards the maxima by moving in the same direction as that of the gradient. Okay, if gradient is in positive direction, we will move in the same direction. On the other hand, if the gradient is in the negative direction, we will move in the opposite direction, that's negative direction. Thus, we reach towards the maxima after optimization. So this is what we use to update the weights when we consider the probability as the optimal function to be optimized. And now let us see how to find now. So instead of j here, what we have in this formulation is p of yk given xk. Right? Let us see here, how do we optimize this? To optimize this, what we need to find is dou p of yk given xk by dou w. Before we do this, let us see this, since this p of yk given xk is anyway function of hw of xk, let us also see the derivative of dou hw of xk by dou w. That is, this will be a internal derivative when we perform the derivative with respect to the probability or the likelihood. So thus we will see this as well. And one more aspect to consider here is finding derivative in cases where there is a multiplication and powers. It is more convenient to first apply the logarithm and find the log derivative instead of direct derivative. And thus that the cost function or the optimal function to be optimized can also be scoring function, or the function to be optimized can also be considered as ln of p of yk given xk. Because as we know, ln is log is a monotonic function, and if p of yk given xk is maximized, it's when ln of p of yk given xk is maximized. So both have the same maximum point. So and thus we can also use ln of p of yk given xk for optimization process. And this we L of w, we can write it as L of w in short, as it is function of w. Okay, so now let us see, first write ln of L of w, which is equal to ln of p of yk given xk, which when we expand it, it becomes yk into ln of hw of xk plus 1 minus yk into ln of 1 minus hw of xk, right? Okay, so this function has to be optimized. So what we need to do is dou L by dou W, and we use it. This gradient is used to update the weights as through gradient ascent plus eta times dou L by dou W, right? So now, as we discussed, let us try to find one of the sub-component of this finding this derivative, that is dou HW xk by dou W, because that's needed for as an internal derivative. So now dou by dou W of 1 by 1 plus e power minus W transpose x. Okay. This, if you find, you can see that this can be expressed as, you can find in conventional way, and you can rewrite it later, whole square minus 1 by x square into the derivative of e power minus W transpose x, that is e power minus W transpose x, internal, further internal derivative of it, that is into, sorry, xk here, xk, right? So this can be rewritten in terms of the original function hw xk itself by writing this in terms of two functions, that is 1 by 1 plus e power minus W transpose xk into 1 minus 1 by 1 plus e power minus W transpose xk. Please see here, this and this are exactly same. As you can see, in the denominator you have 1 plus e power minus W transpose xk whole square, and in the numerator 1 gets cancels out, and what you have is e power minus W transpose xk. Please note that this minus is because of 1 by minus 1 by x square, and when you find internal derivative, there is minus xk here. So this minus and minus gets cancelled, and this is exactly same as what you have here. This and this are exactly same. Now please note that same but rewritten. Why is this rewritten in this way? As you can see here, this can be written now dou hw xk by dou W. We want to rewrite in terms of hw of xk itself. Okay, this is hw xk into 1 minus hw xk. This is one of the important results or widely used result. The reason being, this is the sigmoid activation function. If usually people also denote, instead of hw, people denote with sigma for sigmoid activation. Sigma of x power k is a short notation for this. Sigma w of x power k you can consider sigma into x power k. So if we consider this as hw xk as a short notation, this can be written as sigma into 1 minus sigma. Okay, please note that sigma here is a function, okay, of this, and this is exactly equal to hw. Okay, so this is one of the well-known and widely used partial derivative. So now, given this back small derivation, let us see how does the derivative dou L by dou W will be. So dou L by dou W now, if when we want to find yk into what we have 1 by hw of xk, because as you can see, that's ln of, here you can see ln of hw of xk into internal derivative, what's that, hw of xk into 1 minus hw of xk. I suggest you to do again yourself. I'm just directly writing the terms plus the second one, it is 1 minus yk into 1 by 1 minus hw of xk, okay, which is there in ln, into internal derivative of 1 minus hw of xk is nothing but with a negative sign hw of xk okay, into 1 minus HW of xk, right? So now let us see whichever will cancel out, and then we can write the remaining things. Okay, so and hence if we now simplify this, yk minus yk into HW of xk minus HW of xk, okay, plus yk into HW of xk, right? So you can see that these cancels out, and hence the dou L by dou W, what we have is, please note that W is a vector, okay, yk minus HW of xk. Please also note that here I have W is a vector, that's why we are written here as an internal derivative, okay, W transpose xk is xk, with negative sign, whatever we have here, right? And thus, given the gradient ascent for the update of W, what we have W is Wt minus eta times plus eta times here, okay, yk minus HW of xk, okay. Are we missing something here? So please note that the please note here. So what we missed writing here is xk. So along with this, we have actually into xk as well. Okay, so that's left out here. So here, for a sigmoid activation function with, say, if we consider sigmoid activation function purely as sigma of x is equal to 1 by 1 plus e power minus x, then ideally it is sigma into 1 minus sigma. However, here it's not x, it is double transpose x. So and hence you have here xk as well. Okay, in this expression, in this particular expression. Okay, please note that. Okay, this is for a when this is only function of x. Okay, so when there is a W transpose x for the, as you can note here, the sigmoid function here has W transpose x in the exponent. Okay, because of that, this xk is also coming out. Fine. So I'm now this all has come along with xk into xk everywhere. Okay, and hence this all into xk. I will let me take it out. Please note xk is a vector, whereas all the other elements are scalars. Okay, into now xk. Okay, and then xk will come here, right? So this is what is the final result of regression, updating the regression parameters. Right, and these, please note that this kind of expression for update of weight vectors we have also seen earlier. So when did we see? If we see much before for the this for logistic regression, whatever we have seen, but if we see for the conventional regression, we have exactly the same expression. So here, if we rewrite this, if I rewrite this, Wt plus 1 is equal to Wt plus eta times yk minus W transpose xk into xk, right? So this also has the exactly same expression. This is regression. Okay, so this expression and this expression, whatever we have got currently, are exactly same. But however, what is the difference? Here, please note that this is in some sense HW of xk. Okay, so the key difference between the logistic regression update equation and the conventional regression update equation is that this HW in this is, please note that HW of xk is equal to 1 by 1 plus e power minus W transpose xk for logistic regression. Okay, whereas this HW of xk is equal to W transpose xk only for linear regression. Okay, so whatever we have derived here is logistic regression, right? So please note that the logistic regression tries to map the output variables to 0 or 1. So then yk also will be here for logistic regression. Yk can take 0 or 1. Okay, typically, and here yk is real. Okay, any real number, right? So, but the update equations are same for either logistic regression or for the linear regression. So we can say this is in regression update equation, right? So we keep updating the parameters. We'll stop the update or convergence happen when Wt plus 1 minus Wt, okay, for all the elements is less than epsilon. Okay, so the either norm or individually for each element is less than epsilon. Okay, and at that time we can find out the estimated value of YEST, estimated value of YK for test sample. We can find it out as HW of X test sample, right? So this framework is in some sense is applicable either for classification or for mapping the feature values to any real number, that is estimation of cost or any real parameter. Okay, thank you. Before we conclude, I just want to mention that this regression not necessarily be linear regression or logistic regression. We can also regress with nonlinear mapping between the feature values and the output. Say yk can also be related as w1 into x1. Say if we have x being a simple example having 2 dimensions x1, x2. Okay, and it is kth sample anyway. So I can map it as x1 first element xk plus w2 or w11 into x1, w12 into x1 whole square plus w13 into x1 whole cube plus w21 x2 plus w22 x2 whole square plus w23 x2 whole. Okay, and so on. So not necessarily 3 times, it's up to us. So this is in some sense one example of nonlinear regression. In that case, the cost function will be this yk hat, yk minus yk hat whole square. Okay, if it is first we do it for one sample, later we can also do for, if we wish, we can have the cost function for n samples. And this, if we do for one sample, this is referred to as stochastic gradient descent. Okay, we can, same framework can also be used for batch gradient descent, just having a summation over xk in the cost function, and subsequently it reflects here, right? Okay, so we'll conclude the discussion here, but either linear, non-linear or logistic regression, most of them are formulating the cost function and then updating them, or finding out the partial derivatives with respect to the weight vectors and updating the weight elements by gradient descent. Thank you. Thank you.